Now let's proceed to the fluid measurement. So we have three device coefficients, that coefficients of discharge, coefficients of velocity, and the coefficients of construction. First is the coefficients of discharge. Its formula is C base of D is equals to actual discharge over theoretical velocity. Then the second coefficient device is coefficient of velocity, which is C of base of D is equals actual velocity over theoretical velocity. And the last one is the coefficients of construction, or C to the base of C is equals to area of stream or jet over area of the opening. Now let's proceed to the head loss. First, let's define what is head loss. Head loss refers to a measurement of energy dissipated in a fluid system due to friction, along with the length of the pipe or hydraulic system, and those due to fitting, valves, and other system structure. The total head loss of a fluid as it moves through a fluid system is the sum of elevation head, velocity head, and pressure head loss. So this head loss is unavoided in real fluid system containing liquid or gases. So it is a result of friction between the wall of the pipe and the fluid. The friction between fluid particles as they move relatively to one another, and the turbulence that is caused whenever the fluid flows is directed or obstructed in any way by components such as piping entrance and exit, pumps, valves, and fittings. So you can see the equation of head loss on your right side. We have the theoretical velocity is equals to the square root of 2 times g times h. The actual velocity is equals to c, the base of v, times square root of 2g times h, and the theoretical discharge is equals to a times square root of 2g times h, and the actual discharge, or q, is equals to c times a times square root of 2gh. Our head loss formula is h is equals h plus v sub a squared over 2g plus p sub a over y minus p sub b over y. Now let's proceed to orifice. An orifice is an opening, usually circular, with a closed perimeter through the fluid flows energy equation between 1 and 2, neglecting head loss. E sub 1 is equals E sub 2. So this orifice plate is a flow measurement, an unexpected yet effective primary sensing element. The concept of disarming simple place a restriction in a pipe, then measure the resulting pressure drop across the restricting to infer flow rate, as we can see in the figure above. Now this is the process of the orifice. To get the formula, we have v sub 1 squared over 2 times g plus p sub 1 over y plus z sub 1 is equals v sub 2 squared over 2 times g plus p sub 2 over y plus z sub 2. In that case, that will be v sub a squared 2i over 2g plus p sub a plus y times h over y plus 0 is equals v sub 2 squared over 2g plus p sub b over y plus 0. And that will be v sub a squared over 2g plus p sub a over y plus h is equals v sub 2 squared over 2g plus p sub b over y. The next, that will be v squared over 2g is equals h plus p sub a over y minus p sub b over y plus v sub a squared over 2g. To get the formula of orifice, we have v is equals the square root of 2g multiplied by h plus v sub a over 2g plus p sub a over y minus p sub a over y. Now we have a nozzle. A nozzle is a converging tube installed at the end of the pipe or hose for a purpose of increasing the velocity of the ensuing jet, as we can see in the figure 5 above. So the discharge through the nozzle can be calculated using the equation q is equals to c times a sub n multiplied by 2 square root of 2g times h, where h is the total head at the base of the nozzle and a sub n is the area at the nozzle up. Now we can also see above the unsteady flow of the equation. Now let's proceed to the weir. So weir is an overflow structure which is built across an open channel for a purpose of measuring or controlling the flow of the liquid. Weir have been commonly used to measure the flow of water, but is now being adapted to measure a flow of any flows of water of our liquid. So based on the picture or based on the text, the weir is a barrier across the width of the river or the dam that alters the flow's characteristic of water and usually result in the change of the height of the river. So they are also used to control the flow of the water of the outlet, lakes, ponds, and reservoirs. We have a classification of weir according to its shape. Weir may be rectangular or triangular, trapezoid, circular, or parabolic, or any other regular form. Now we have a Francis formula, which is C to the base of W is equals 1.84 multiply by 1 plus 0.26 multiply by H over D squared. That will be our SI unit. Now we also have the Redbook and Chow formula. In English unit, we have CW is equals 3.27 plus 0.40 H over P, while in our SI unit, we have CW is equals to 1.8 plus 0.22 H over P. We also have a basin formula, which is C base of W is equals to 0.5518 multiply by 3.248 plus 0.02161 over H multiply by 1 plus 0.55 times H over D squared, as we can see in the equation above. Next is the contracted rectangular weir. So the effect of length of the contracted weir is given by L is equals to L exponent of 1 minus 0.1 in H, where L is measure of the length of the crest, N is the number of the end contract 1 or 2, and H is for the measure of head. So we can see the contracted rectangular weir picture above there. We also have a triangular weir or the V-notch. So it is a very low head. The nap of the rectangular weir has a tendency to adhere to its downstream face. Its equation is Q is equals to 4 over 15 multiplied by C times square root of 2G multiplied by L times H raised to 3 over 2. Then it will become Q is equals to 8 over 15 tan theta over 2 minus H raised to 5 over 2 is equals to C base of W tan theta over 2 minus multiply by H raised to 5 over 2. For the standard 90 degrees weir, its SI unit is Q is equals to 1.4 H raised to 5 over 2, while in English unit, it is Q is equals to 2.5 H 5 over 2. Now let's move on to the trapezoidal sharp-crested weir. So first, let's define it. The discharge of the trapezoidal weir is assumed as the same as that from the rectangular weir in combination. So we can see it. The picture above is the trapezoidal sharp-crested weir. So move on. While the hydraulic similitude, it is an indicate of a relationship between a model and a prototype. Now let's move on to the geometric similarity, kinematic similarity, and the dynamic similarity. First, let's define the geometric similarity. So, or same length scale ratio, a model and prototype are geometrically similar if and only if all body dimension in all three coordinates that has the same linear scale ratio. So when we say geometric, it means shape. So the model and the prototype should be the exact same shape. Second is the kinematic similarity, or the same length scale time scale ratio. A motion of two symbols are kinematically similar if homologous particles lies at homologous point at the homologous time. So when we say kinematic, it is movement or motion. So the model and the model and the prototype should be at the same speed or the same kinematic movement. The last one is the dynamic similarity, or the same length scale, time scale, force scale ratio. So in the model and prototype force and pressure coefficient are identical. So it means that the prototype is equals to the model overall. Now we have the dynamic similarity for compressive flow. RE prototype is equals to RE model. RE means Reynolds number. MA prototype is equals to MA model. MA means mass number. And the K prototype is equals to K model. K means specific heat ratio. Now we have for incompressible flow, we have two types. Letter A, the no free surface, and letter B is the with free surface. For no free surface, we have our Reynolds number prototype is equals to RE model, while in letter B with free surface, we have Reynolds prototype is equals to Reynolds model. The WE stands for Weber, so Weber's prototype is equals to Weber's model. FR means fraud, so fraud prototype is equals to fraud model. The CA prototype, CA means the quotation number, or CA prototype is equals to CA model. The CD prototype, or CD means drag coefficient. Drag coefficient prototype is equals to drag coefficient model. Next up is the dimensionless group in fluid mechanics. Now in this table, we will see the dimensionless group in fluid mechanics. We have the parameters: Reynolds number, mass number, fraud number, Weber's number, gravitational number, Prandtl number, Eckert number, specific heat ratio, Strauss numbers, roughness ratio, Grashof numbers, temperature ratio, pressure coefficient, lift coefficient, and drag coefficients. Now we have the dimensional analysis. Dimensional analysis is a method for reducing the number and complexity of the experimental variable which affect a given physical phenomena. We have the Buckingham Pi theorem. Step 1, we have to write the function and count variable n. Step 2 is the least dimension of each variable. Step 3, find j. Step 4, select repeating j variable. We can use letter A, flow quantities, letter B, property of fluid, letter C is the dimension. In step 5, the number of pi group is less than or equals to k is equals n minus j. So determine the pi group. Now let's proceed to the dimension of fluid mechanics properties. So as we can see in the table, we have the quantities, the symbol, and the ml, t, delta, theta. So we have the quantities: length, area, volume, velocity, acceleration, speed of sound, volume flow, mass flow, pressure, stress, strain rate, angle, angular velocity, viscosity, kinematic viscosity, surface tension, force, movement, torque, power, work, energy, density, temperature, specific heat, specific weight, thermal conductivity, and expansion coefficients. Now we have our example 1. Calculate the discharge through the 140 mm diameter office as shown in the figure. Assume C is equal to 0.62. So we have two formula. The Q is equals to C times A times the square root of 2 times gravity times height. And the H is equals to H upstream minus H downstream. Now let's calculate for the height. We have 3 plus 50 over 9.81 minus 15 over 9.81 for the total of 6.568 meters. Next, let's solve for the Q. We have Q is equals to C times A multiplied by 2 times the gravity times the height. So we have 0.62 multiplied by pi over 4 multiplied by 0.14 squared times the square root of 2 times the gravity, which is 9.81, and the height of 6.568 for the total of 0.108 meters cubed per second. Now, example number 2. Water flows through orifice at the vertical side of a large tank under the constant head of 2.4 meter. How far horizontally from the vena contracta will the jet strike at the ground 1.5 meter below the orifice? We can see the given in the pictures. We have the height of 2.4 meters and the y of 1.5 meters. We have to find the x. Now let's proceed to the solution. We have y is equals to x tan theta minus g times x squared over 2 v0 squared cos squared theta. So our y is negative 1.5 meters. Now we have VO is equals to square root of 2 times gravity times height. So square root of 2 multiplied by gravity of 9.81 multiplied by 2.4 for the total of 6.62 meters squared. Our theta is equals to 0. Now let's proceed to find the x. We have negative 1.5 is equals to x tan 0 minus 9.81 times x squared over 2 times 6.862 squared cos squared 0. And the answer is 3.79 meters. That's all for Module 5. Thank you for watching.